classify those normalized doublets according to the value of B0. So you see this, it's natural definitions. We have all the normalized doublets, and here we classify according to the B0. And we define D and J according to this. What can we say about those polynomials? And where we can say many things, I'm going to show you a long recurrence relation. I will show you, please don't take note of this recurrence relation because it has too many lines. But what is interesting is the fact that it has special values which are very relevant to classical notion. Okay, well, we can forget about this. Okay, so we can place now the Doubloon polynomial triangle like this. So this is the geometric function for normalized doublets that for which B0 equal to 2. This is the normalized doublets for n equal to 2, for which B0 equal to 3, and so on. We can place this in a triangle. And here you have the values, you see. So in other words, we do have a triangle of polynomials. And, oh, no, well, no time to, but, okay, now, this is the recurrence relation we can work out. That's a lot of work. Okay, we can forget. In other words, there is a recurrence relation on those polynomials. We do not have a recurrence relation on Dn, on the sum of those polynomials, but we have a recurrence relation for the entries. Okay, now, two important cases because there are people, oh yes, okay. We have various specialization. So here is D and Q. So those are polynomials in this triangle before. So what the game we can play? We can play the game Q equals 0. Then we have an integer. We can play the game Q equals 1. We have another integer. Then we can add up all those integers, all those polynomials. And if we do this, here we have the D and Q, which is here, that D and Q, which is related to the coordinates. You see, when you replace T by minus Q to the minus 1. And here, you know what this is? C stands for Catalan. So this is the Catalan. Tn is a reduced tangent number. So we have all this. But we have more. And then for Dn equal to 0, okay, we have the Catalan. Oh yes, it's, you know, we don't have to think. You see, this, you know, this things for you. So okay, left and the right top rows into recurrence form. Okay, now. Okay, now. When you have Q equal 1, we have a recurrence like essentially this. This is the other thing to remember of this. I'm going to illustrate in a moment. So in other words, if you replace Q by 1, we have this. And this was found by Poupard. This is a Poupard.
Now, with a different meaning, right?
No, different meaning.
Yeah.
But first of all, we have this. She worked out this, and she calculated the function for this triangle. She does, which is also valid for our model. Yeah. And this is a Poupard triangle. And you see the sum in each row is this. You have the reduced tangent. So this simple enough. I think I will illustrate in a moment the Poupard triangle. You have P 104. Okay, 104 is here. 104. Minus 294. Minus 294. 104. Minus 294. Plus 68. So this one. Minus twice this one on the left, plus this one is equal to this one. Okay, so we have a reconciliation for those everywhere. And if we have this is what you prove, and that we have the reduced. But that's difficult to, when you have this reconciliation, to prove that you have the reduced tangent number. This is what you have done. And now when you have q equal to 0, we have the Catalan triangle. Actually, I didn't know what the Catalan triangle was, you see, before learning this. And so when you, and this is very simple. In that case, look at this. Very simple. Do I have the Catalan? Yes, I have the Catalan triangle. So this is known to many of you. You see, I didn't know this. So 1 plus 1, 2, 2, 2, 1 plus 1, 2. You see, 5, all 5, 3, 1. Okay, no problem. Or is it 14 is equal to 9 plus 5. Catalan triangle. And here we have all 0. All 0. So we have a sequence of a triangle of polynomials and two special cases. For q equals 1, we have the Poupart. For q equals 0, we have the Catalan. 3 minutes for open questions. Okay, I think I will make it. Okay, the Poupart. Now I come to Poupart. Okay, that's a good, I should have showed you this. See? The Poupart speak of strict ordered binary trees. And let me hold sort. Sort, strict. This is what? F is decreasing. The preimage, either X has no preimage or two preimages. And for each X, if sooner or later, the iterate of F is equal to 1. Okay, it's better to understand this. Poupart. You see, here you have the four subs. 4 subs. See? The number of subs follow 2 plus 1 such that equal to j is equal to d and j of 1. So this is what Poupart have done. And not only this, she has calculated the genetic function. I don't have it on my slides. Okay. Well, I think I will make it. Now I come to my point. You see, what? Let sub be the set of all the subs of row 2 plus 1, such that we have this. Remember this. We have 1 that start 2 plus 1 here is 1. 2 plus 1, you see, the image of 5 is 2. The image of 5 is 2, or 5 is 3. The image of 5 is 1. So we have 1, 2 of 2, and 1, 3. Okay? So this is Poupart. And now, the fact is, find a bijection of the doublets for which P0 equal to J to the model of Poupart. We don't know the natural one. We know that's the same. We do not know. I know the second question, so this will be interesting to see this, because it has to, we have to be inventive. We have 2 models in the Q model, but we do have the statistics for the doublets, but nothing for the sort. Find 1. There is 1. There is 1. We must find a natural one. And the third open question, which is not mentioned here, find a genetic function. We have a genetic function for d and j of 1, but we do not have a genetic function for d and j cubed. So it has to be found. So this is really in the spirit of what Doubloon and his followers do. They must find things which are missing here. we have not completed our work. So I think that I will start.
Thank you very much. You will be glad to answer questions in private. Thank you very much. If you'd like to join us for dinner at 6:45, let me know right away. Right now. Thank you.